Hi all, today we're going to be learning how to analyze the association between two categorical variables. So as you can see, I have the lab open, the PDF file, and also I have the NC birth dataset open as well. So let's get started from the beginning of the lab. One thing I wanted to show you guys first before we get into the chi-squared is dealing with a 2x2 contingency table and looking at odds ratios. So we learned how to do a contingency table in the probability lab, if you guys recall, and also when we looked at comparing two proportions. So let's create this 2x2 table that we see here with the SPSS dataset. So this is crossing smoke during pregnancy and low birth weight. So let's go to SPSS and we go to our Analyze menu, Descriptive Statistics, Crosstabs. So we see the list of the variables on the left-hand side, and let's put low birth weight in our columns, and let's put smoke during pregnancy in our rows. And we can click OK, and we can take a look at the counts within the contingency table. One thing I wanted you guys to notice was the arrangement of the variables here. You can see mother did not smoke during pregnancy is on top, and mother did smoke during pregnancy is on the bottom, and here on the left hand side infant was not low birth weight, infant was low birth weight. If, for example, you were interested in arranging this table differently, and typically what would be the arrangement would be mother did smoke during pregnancy, here the exposure, and then the outcome infant was low birth weight would be here, infant was not low birth weight would be there. It doesn't make a difference when you're calculating. You would calculate the odds ratios using the appropriate values within the table, but just if you prefer to have the table arranged in a different way, SPSS arranges them in ascending order. So the coding here for infant was not low birth weight is 0, and the coding for infant was low birth weight is 1. So it's arranging it in ascending order, and the same thing here. Mother did not smoke was 0, and mother did smoke during pregnancy was 1. So if I wanted to change the arrangement of this table, and this also goes into a little bit of data management techniques in SPSS, so this should be some useful information perhaps. What we can do is change the coding of the variables. So if you remember, in the variable view, the values tell us what the data values represent. So for instance, smoke was, you see we have 0 and 1s, and low birth weight we have 0 and 1s as well. So to understand what those values indicate, we go into variable view, we go to values, and we see 0 indicates mother did not smoke during pregnancy, and 1 indicates mother did smoke during pregnancy. And the same for low birth weight. We see here 0 indicates infant was not low birth weight, and 1 indicates infant was low birth weight. So what I want to do is make all the zeros be 2s. So what I can do here is go to transform, and I'm going to ask it to, before I do that, I want you guys to take a look here. You see again in smoke that there's 0s and 1s, you see all these 0s, and low birth weight, you see all these 0s and there's 1s. So I want you to see what will happen once we do this. So we'll go to transform, we're going to recode into the same variable, which means that the recoding that we do will change the values for the value smoke will remain, and the values will change. The zeros will change to 2s. Let's say I wanted to keep this variable smoke and create a new variable with new values. You can just do recode into different variable, and you would need to make a different variable name, for instance smoke new or smoke 21 or whatever you wanted to name it. And then you can just look at the two variables side by side, and you'll see that all your zeros would have changed to, in this case, a 2, and the 1s would remain 1s. So you would have a new variable, and with the values recoded as you wish. So in this case, I'm going to recode into the same variable. So the smoke variable itself will change. So I'm going to click on that, recode into same variable. And the variables that I'm interested in recoding is low birth weight and smoke during pregnancy. So you're going to want to click on this here, old and new values. So the value of 0 I would like to change to a 2. So I just click add. So this is saying the old value will be 0 and the new value will be a 2. And I click continue. Now I need to do that for the other variable as well, old and new values. So the change that we made previously is entered already. So we can keep that the way it is. And we can click continue. So what happens now when we click OK, we can see here in our output on the bottom the syntax. It says it's a pretty simple syntax. It's saying recode. You're putting your variable names. One was low birth weight, the variable name was low, and the other one smoke. And within parentheses we're telling SPSS to make all zeros equal 2. And then we write execute. This is the syntax associated with this. So let's look at our data set now. And we can see here that in smoke all of our zeros became 2s, and in low birth weight all of our zeros became 2s. So now when we do a crosstabs, we'll have it arranged in the way we wanted it to be arranged. We have mother did smoke during pregnancy, infant was low birth weight. Now notice that we don't have a label here. You guys notice this? It's just telling the number 2. What we would need to do, if you remember, the codings here need to be changed. We still have the codings the way they for the previous values. So smoke during pregnancy 0, this needs to be a 2. And we click change and we click OK. And the same thing for low birth weight. This needs to be a 2, 0. Change that to 2, we click change and we click OK. So now we'll go to Analyze, Descriptive Statistics, Crosstabs, and OK. And now you see our labels are there. So what we have here is our crosstabs, and now it's arranged the way we want it. We have the exposure on top, mother did smoke during pregnancy, and the outcome, infant was low birth weight on the left side. So to get odds ratios, what we would need to do is click on Analyze, Descriptives, Crosstabs. Now for statistics here, we want to check risk. So make sure that's checked and click Continue, and now click OK. And what you'll see here is this extra piece of information giving us an odds ratio and a risk ratio. So what you can do manually with this 2x2 table, we can basically calculate these odds ratios on our own. It's a simple calculation. We can enter our data, first of all, 15, 55, 99, 629. So this is smoked. This is did not smoke. This is low birth weight. Yes. And low birth weight. Oops, sorry. Low birth weight. And then we can sum our rows. We can do our sum function. Sum up our rows. We can sum up our columns. So we see here we have the marginal totals and they're the same as SPSS. You can see here. So what we do to get an odds is we divide our count for low birth weight equals 15 by our count for not low birth weight, 99. So that's the odds of low birth weight among those who smoked. Now we want to know the odds of low birth weight among those who did not smoke. So we calculate that, 55 divided by 629. So this is odds. We can calculate risk. Now keep in mind this is a cross-sectional survey, so risk is not appropriate for this case. Risk is appropriate for a longitudinal analysis where we are able to observe incidence of outcomes. So in this case it's not appropriate, but you can still simply calculate it. Risk is simply the probability. In this case it's 15 divided by 114. So it's the probability of low birth weight given smoking. So if you guys remember the probability labs, the conditional probabilities, this is simply a conditional probability. It's the probability of low birth weight given that a mother smoked. So that is 15 divided by the total, which is 114. And then we have 55 divided by the total, which is 684. So the odds ratio, the risk ratio, is simply dividing the odds of low birth weight among those who smoked by the odds of low birth weight among those who did not smoke. So we take this value here, we divide by this value here, and we end up with 1.73, and we see here in our SPSS output 1.733. So this here is telling us the odds of low birth weight in those who smoked relative to those who do not smoke. So now keep in mind this is a relative measure of effect. We're dividing here. This is just telling us the odds of low birth weight in those who smoked relative to those who did not smoke. So it's 1.7 times higher. The odds is 1.7 times higher. And the risk ratio can be calculated similarly. And we see here it's 1.63, and we see that value here. This is the risk ratio. If this was not a cross-sectional analysis, we can look at risk ratios. In this case, what we want to focus on is this top row here, odds ratio. Now we see another piece of information here, a confidence interval for the odds ratio. Now if the odds were equal, we would end up with an odds ratio of 1. So the null hypothesis is that the odds are equal in the population. So what this is telling us is that the 95% confidence interval contains, in this case, the value of 1, which means that it's possible that in the population the odds are in fact equal. So we can't conclude that the odds are different. We see that our data shows that the odds is higher in smokers, but the confidence interval is more useful. It's telling us what we want to know in the population, from which the sampling distributions for these two groups. There's one sampling distributions sampling distribution from others who smoked and 1 sampling distribution from others who did not smoke. And we want to determine whether the centers of these sampling distributions are equal, basically. So in this case, we can't assume that they are different. This is saying that that there's a possibility that the odds ratio is 1 in this case. So we can't conclude that these two variables are associated, smoking and low birth weight. So that's how we would calculate an odds ratio, and that's how we would interpret the confidence intervals. So remember, look for a value of 1 within the confidence interval. If you see a value of 1, we can't assume a higher or lower odds in the population. Now, similarly, we could look at the proportions. If you guys remember, in the lab and lecture, the class where we compared proportions for two groups, we did the same example with the same 2x2 table. We have a proportion from others who smoked, and we have a proportion from others who did not smoke. And we can do our z-test and get a p-value the same way we had done previously. If you guys go back to the lab, the z-value was 1.79, and the p for that was 0.074, which is higher than our alpha of 0.05, so we failed to reject the null, meaning that these two population proportions we cannot conclude are different. So this is our alternative, and this is our null, and we failed to reject the null. A third way to look at this is with a chi-squared. So we can look at a 2x2 table with a chi-squared analysis as well. So if we go to SPSS and go to Analyze, Descriptive Statistics, Crosstabs, for statistics we can click on chi-square, and we'll get more into chi-square in a moment. Click Continue, click OK. So what we end up getting here is a chi-squared test result, and we notice here on the top row is what we're interested in, the chi-squared value of 3.197 with a p-value of 0.074. Notice that the p-value is exactly the same as that for the z-score. When we had done the test of proportions, we had a z-score, our test statistic, and the p-value for that z-score is 0.074. So we see here that for the 2x2 table, the results of the chi-squared test and the test of proportions and the odds ratio are all equivalent. So we looked at this 2x2 table 3 different ways. So now we're going to move on to dealing with a variable where there are more than 2 categories. So this here we see as a 2x2 table. We can also deal with 3x2 tables, 3x4 tables, any size table using a chi-square test. And the chi-square test will tell us overall if the two variables are associated. So if we scroll down in the lab, this is some more information about chi-squared and the equivalence of the 2x2s when you do a z-test and a chi-squared test. You can read this section on your own. Moving down more, we see here a table where there's more than 2 categories in our row. So in this case, obviously, we wouldn't be doing odds ratios. We could do pairwise odds ratios. We could do pairwise tests of proportions. But for this lab, we're going to learn how to do chi-squared test for the association between ethnicity and marital status in this case. The chi-squared test is an omnibus test. It's going to tell us overall whether these two things are independent. So if you guys remember the probability lab that we had done, in the end of the lab we did a test of independence. Now the test of independence was done on the sample data. The chi-square test is an inferential test. It tells us what we want to know about the population. So it's a hypothesis test, and we're going to get a p-value. The probability lab, we didn't do a hypothesis test. We simply looked for independence with our sample data. What we want to do now is do a hypothesis test and make inferences about the population. So what we want to know whether ethnicity and marital status is in fact associated. So we can see here the assumptions of a chi-square test. So this is a reference to the optional textbook for the class. One, obviously, categorical variables and random sampling, and expected counts of greater than or equal to 5 in all cells. So it should be that these counts in all cells should be greater than 5. If not, we can do what's called an exact test, but that's not something we're going to cover today in this lab. And we do, in fact, not violate that assumption here. So what we'll do is move on with the chi-square test, and here's some extra reading that you can take a look at. It's just it's tying this all back to our probability lab. So let's move on and let's start the chi-square test and see what we find. So the first thing, remember, is what you want to be able to do is know how to write your null and alternative. In this case, our null is simply that marital status and ethnicity are independent. Our alternative is that marital status and ethnicity are associated or dependent. In SPSS, we're going to open that up. We're going to go to our Analyze, Descriptives, Crosstabs. Now we're going to move these out of the way, and we do ethnicity. We'll put in our rows, and we'll put marital status in our columns. And remember, in the statistics area, we want to calculate chi-squared. And I'll keep risk checked just so that you can see what happens with a table that's larger than 2 by 2. It will not give you odds ratios. So we see here risk estimate statistics cannot be computed. They are only computed for a 2 by 2 table. So in this case, we are not able to get odds ratios. But again, we can, do pairwise odds ratios manually if we were interested in doing that. In this case, we see here the results of the chi-square test. We can see our contingency table here, and actually the order of this is not the way it is in the PDF. Let's switch that. In the PDF, it's in the rows, not the columns. It doesn't make a difference for the chi-square test, but I just want it to be arranged the same way. So this is consistent with the PDF file. So let's go back here and look at our output. So we see our counts here, and we see the chi-square test result. We see our chi-squared value, and we see our p-value. Our p-value, assuming our alpha is 0.05, is less than that. Therefore, we are able to reject the null hypothesis, and we could conclude that ethnicity and marital status are in fact associated. Now notice in the PDF file we have something here called expected counts. So we can ask SPSS to give that to us by going to our Analyze, Descriptives, Crosstabs. When we click on cells here, we see here under counts there's an option for expected. We can click continue once we have that checked, and now we have what are called expected counts. Now again, tying back to the probability lab, if you recall, for independent events, the probability of A and B, meaning the intersection here of a cell. So let's say the event A is non-Hispanic white, and let's say the event B is married. So the probability that both of these occur is the intersection here. And if you recall from the probability lab, the probability of A and B equals the probability of A times the probability of B. This is the case for independent events, right? We could calculate the probability of A here. What is the probability of A? The event A, we said, is non-Hispanic white in this case. So what would the probability be for this event, non-Hispanic white? It would be the marginal total, 523, divided by 800. So we can calculate that, 523 divided by 800. We can also calculate the probability of B, married, which is 537, the marginal total divided by 800. 537 divided by 800. So now if these events were in fact independent, the rule is that the probability of A times the probability of B would equal the probability of A and B. So what we can do now is multiply these two values together to get the probability of A and B, assuming independence. So we can say this one minus this one here. So that's what the probability would be for A and B if these two events were independent. Now I want to get a count from this, so I can just take that and multiply it by the total 800. And we see here 351.0638. What we see here in our SPSS output, 351.1, it's rounded off. So that's the expected count. If these two events were in fact independent, that's what the count would be using this rule, the probability rule. Now there's a shortcut to do this. We can use this shortcut here, which is in the lab. It's the row total. So the row total, 523, times the column total, 537, divided by the grand total. It's equivalent to what we just did, and you end up getting the same value. So we see here 351.1. So you can do that for each individual cell to get an expected count. So what the chi-squared test is testing is how far off are the observed values compared to the expected values. How much do we deviate from independence overall? Remember, overall, it's not telling us anything about individual cells or anything. We're going to get into that in a second. So that's why it's called an omnibus test. And this is the formula that you would use by hand to calculate that. For each cell, you would take the observed minus the expected. You would square that value and divide by expected. So we see here that each cell's values are entered for you into this formula, and what we end up with is a chi-squared test statistic, 128.288. Let's go back to our SPSS output and confirm that that's the value that was obtained. We see here 128.388, so there's some rounding error that occurred, but we have the same result. Now, degrees of freedom for a chi-squared test statistic, remember from lecture, is rows minus 1 times columns minus 1. So how many rows do we have in this contingency table? We have 4. So rows minus 1 would be 3. Columns in this case is 2, so 2 minus 1 would be 1. So our degrees of freedom would be 3 for this test. Now, to get a p-value for our chi-squared test statistic, in Excel, we can simply enter equal sign and start typing in chi-square, and we want to do chi-square distribution right tail, and it's asking for the chi-squared value, so 128.3, and it's asking for the degrees of freedom. And we see here that the p-value is 1.26 times 10 to the negative 27th. That's very, very small. It's well below 0.05. We can definitely see that these two variables are in fact associated. and SPSS also gives us that value, but only 3 digits. So with Excel, we're able to get the exact p-value for the test statistic, the chi-square test statistic. So we can conclude from this chi-square test that we are able to reject the null hypothesis. So this null hypothesis, marital status and ethnicity are independent. We are able to reject that and conclude that marital status and ethnicity are associated. Now the next section of this is going to tell us information about individual cells. So remember, the chi-square test does not tell us which or how many cells deviate from independence. It's just telling us overall that the two variables are associated. We would be interested in knowing which variables, which cells in this case, which events. So there's several different events here. There's non-Hispanic white, there's non-Hispanic black, Hispanic other. We would like to know which ones deviated from independence. So what we can do, one thing that we can do, is do a residual analysis. So residual is simply the observed minus expected. Excuse me. So in the table, the observed value, for example, in this case is 417. The expected value is 351.1. So the difference between that is the residual. So what we can look at in SPSS are what are called standardized residuals. So I'm not going to, there's some reading here that you can do on your own to get some more information about standardized residuals. Also, a PDF was sent out via email for a chapter that has some more information about that as well. So you could look at that on your own. The only thing you just need to know here when you look at your standardized residuals, just like in a normal distribution, because we're assuming the standardized residuals are normally distributed, we want to look for values that are very unexpected. So remember, in a normal distribution, approximately all of our data should fall within 3 standard deviations, remember? And about 95% within 2 standard deviations, about 68% within 1 standard deviation, etc. So what we would like to know to determine which cells deviated significantly from independence is the value for the standardized residual for that cell. So in SPSS, we can go back to our Analyze, Descriptives, crosstabs, and for cells here, there's an area for residuals. So click on Standardized, click Continue, click OK. So what we have now is an area for standardized residuals. Each cell, it's giving us a value. So we can see here that we have some large values here. Now what's the cutoff? In this case, I'm saying to use a cutoff of 3, because remember, in the normal distribution, all of the variables should fall within 3 standard deviations. All of the data, should fall within 3 standard deviations. Data that falls beyond that would be considered unusual. So we should look at our output cell by cell here and look for values greater than 3. So we see here a 3.5, we see a -5, we see a -5.3, we see a positive 7.6, we see a -1.1, 1.5, -0.3, 0.4. So the sign of the residual simply tells us whether the expected count was higher or lower than the observed. So in this case, the observed count was higher than the expected, therefore the residual will be positive, and the standardized residual will be positive as well, and vice versa. When the observed count is lower than the expected count, the residual will be negative and the standardized residual will be negative. So these cells here we see are contributing to our chi-squared test being significant. These cells are deviating from independence significantly here. We can see that there's a large deviation from independence in these cells in particular. For these cells here, we don't see very large deviations. We can see here the observed count was 10 and the expected was about 9. It's not a very large standardized residual. You can see it's 0.4, in this case negative 0.3. These observed counts were not very different than what would be expected if these two events are independent. These, however, do deviate significantly from what would be expected if they were independent. So that is how you would conduct a residual analysis to get more information about particular cells and categories. The chi-square test, remember, does not give you that information. It only tells you overall. It's an omnibus test. It tells you overall whether the two things are associated or independent, and the residual analysis is useful to use as a follow-up to that. If you get a significant chi-square test, you should conduct a residual analysis. And another thing that we can do in addition to residual analysis is do a pairwise comparison. So a pairwise comparison will basically tell us, recall in the beginning of this lab we did a test of proportions. That's what a pairwise comparison will do. It will do a test of proportions for every pair. So non-Hispanic white versus non-Hispanic black, Hispanic versus non-Hispanic white, other versus Hispanic, etc. It's going to do a test of proportions, same as we learned previously, and also we just reviewed that in the beginning of this lab. It's going to do that for every pair here. It's going to test the proportion of married for every pair and compare it to one another and give us a Z statistic and a p-value. In this case, we could do that by hand and get a Z statistic and p-value for each group, but SPSS will do that for us for every possible pair. And let's see how to do that here. You can go to descriptives, crosstabs, and for statistics, for cells, we see an area here under Z-test, compare column proportions, and we see adjust p-values, Bonferroni method. Now, what ends up happening when you do multiple comparisons like this, you end up having an inflated type 1 error rate. And what you need to do is adjust your alpha level because of that. We'll go more into that with the ANOVA lab, but just recall that when you do one comparison, just one proportion versus another, you set your alpha at 0.05. When you end up doing multiple tests, like we are about to do, you end up having an inflated type 1 error rate, and because of that you need to adjust your p-value. You need to set it less than 0.05 to account for that. And there's different methods of doing that. One of them is Bonferroni method, and that's what's available here for SPSS, so that's what we'll choose. So we'll click continue now, and we'll click OK. And we see here an output here. Now, one thing I want you to look at is the order of this table. So remember that the option in SPSS said compare column proportions. So what this is doing for each row is it's comparing the proportion of married to not married. Right? It's comparing the proportion of non-Hispanic white in married versus not married. Do we want to do that? No, we want to compare the ethnic groups to one another, and the outcome we want is married. So we want to switch this table. So let's switch the rows and columns here. Let's put ethnicity into columns. Let's put marital status into rows and click OK. So now this is what we want to see. So what this is doing now, it's comparing proportions, column proportions. So this column here of non-Hispanic white, it's saying the proportion of married. It's comparing that to every other group, and it's comparing those to the other groups. Now, to make this table even more informative, we can have the percentages, the proportions listed for us here. We can click percentages here, click on column, click continue, click OK. So this is saying within non-Hispanic white, the proportion that are married is 79.7. Within non-Hispanic black, the proportion married is 33.3. Within Hispanic, the proportion married is 57.3. And within other, the proportion that are married is 63.0. So what we will do now is, remember in the beginning of the lab, we did a test of proportions. We were testing proportion of low birth weight in mothers who smoked versus not. That's exactly what we're doing here for every possible pair. We're comparing the proportion of married, and we're doing a pairwise test for every pair here. Now the way to interpret this table, you would look for matching subscripts. So if you notice here, you see here these little subscripts, these little letters C, A, C, B, A, etc. So let's start at non-Hispanic white. So if I started with non-Hispanic white, I see a subscript of A. Any other cell that has a subscript of A, it means that we were not able to reject the null hypothesis that the proportions are different. So for example, let's go one by one. Non-Hispanic white versus non-Hispanic black. Excuse me. Do we see a matching subscript? We do not. We see an A here. We do not see an A here, which means that we reject the null and we conclude that the proportions are in fact different. And which proportion was higher? We can see here 79.7. We can see here 33.3. So this is at an alpha level of 0.05, and this is a two-tailed test. Now non-Hispanic white versus Hispanic. We can see there's an A here, there's no A here, there's a C. We again are able to reject the null hypothesis and conclude that the proportions are in fact different. And we can see here that one is higher than the other. Now let's go to non-Hispanic white versus other. We look at the subscript A. In this case, we see a matching subscript. Therefore, we fail to reject the null. We cannot conclude that the proportions are in fact different. And we can see that the proportions are not as different as the others. So with this case, we were not able to reject the null. Now let's go to non-Hispanic black. We already did the comparison with non-Hispanic white. We do non-Hispanic black versus Hispanic. We can see here the subscripts do not match, and we look at the proportions. Hispanics have a higher proportion of marriage. We conclude that we are able to reject the null, and we conclude that the proportions are in fact different. Non-Hispanic black versus other. We see here we do not see matching subscripts. We are able to reject the null and conclude that proportions are in fact different. We can see that other has a higher proportion. Now let's move on to Hispanic. We would do the same comparisons again. And when we go to other, we would do the same comparisons for each other group, looking for matching subscripts, and that will tell us whether we're able to fail to reject or reject. So what we've done now, we started with a 2x2 table. We saw how to calculate an odds ratio. We saw how to interpret the 95% confidence interval for an odds ratio. We also saw how to analyze a 2x2 table simply doing a test of proportions. So that is an absolute measure of effect. The odds ratio is a relative measure of effect. We also saw how to conduct a chi-square test for a 2x2 table, and we saw that the results of a chi-square test and the test of proportions were equivalent. The p-values were exactly the same, and the same goes for the odds ratio results. For the 2x2 table, you will have equivalent results. And then we saw how to deal with situations where we have more than two categories, in other words, a larger than 2x2 table, and that was a chi-square test. We saw that the two were associated. When we have a significant chi-square test, it's useful to follow that up with a residual analysis, and also we can do a pairwise comparison, which will do a test of proportions for each possible pair. So that's the end of this lab. This is analyzing the association between categorical variables. Next week we'll get into ANOVA, and until then, see you next time.